for our final talk. We are going to have Janina Letz, and she's going to tell us about generation time for tensor products and Koszul objects in triangulated categories.
Thank you. And thank you for giving me the opportunity to speak. And all of you for showing up for this one talk today, which, yeah, I heard there was supposed to be 3 originally, so I'm the last one standing, I guess. So let's see. So, yeah, so the title has a bunch of words I probably have to explain, and I hope none of you are scared of triangulated categories. I try to be gentle. So maybe let's start with something I'm all more familiar with. So let's start with a commutative ring. And let's take 2 R modules. Then we could ask a question, what's the projective dimension of the tensor product of these things? If you make some assumptions, so this is more like a motivating example, but if we assume that the tor between those 2 vanishes in non-zero degrees, then we can know that the projective dimension of M tensor N, we can literally just take their projective dimensions, tensor them together, and they're going to be a projective resolution. So we know this is bounded above by the sum of the projective dimensions. Okay, let's look at a slightly different setting. Let's start with a local ring. So M is the maximal ideal, K the residue field. Then we can ask about the Lowy length. So maybe as a reminder, the Lowy length of a module is the highest power, is the smallest power of the maximal ideal that annihilates the module. So it's the infimum n such that the maximal ideal to nth power times n is 0. And we can ask the same question. What's the Lowy length of a tensor product? And maybe the thing to realize is, maybe let me put it here. If you multiply the sum, we multiply the I plus j power, this is actually the same as putting the first one to m and the second one to n. So this means the Lowy length is bounded by, so this becomes 0 if one of these is 0. So it's the Lowy length of m plus Lowy length of n minus 1. Now I feel like something is slightly off. Okay, maybe, sorry. Now I'm reading this and I'm like, maybe I'll delete this again. Okay, so, but this is definitely true. Okay, so now we have these 2 formulas. They look kind of similar, but they're not quite the same. But that's something we can easily fix. So because the strange thing is, somehow when we look at the Lowy length, we think about M being built out of the residue field. We're basically just taking the residue field, gluing it together over and over again, and we get the module N. And so, but the Lowy length of K is actually 1. While for the projective dimension, we think about it, we're starting with the ring, and we're just doing the ring over and over together. However, the projective dimension of the ring is 0. So there's somehow this offset. So we should, let's fix this, just add +1 to each projective dimension. And we get actually the same formula. Okay, so what is the connection? And yeah, the first thing I already mentioned it, comparing like projective dimension, you can think about it, we're generating a module out of the ring or the projective modules. For the Lowy length, we're building everything out of the residue field. So let's try to make that explicit. And this is where I go on to triangulated categories. So I'll tell you what kind of the most important things are about them that we need. And the reason why we want to go to the triangulated category, or in this case, the derived category of the ring, is we want to allow resolutions. We want to replace m by its resolution and just ask a question about the resolution. So I'll explain the construction in any triangulated categories, but if this makes you uncomfortable, I'll in parallel tell you what all of this means in the derived category of a ring. So feel free to just think about the derived category. And for those who haven't seen the derived category, or maybe as a reminder, the objects are complexes, and the morphisms are chain maps, so they have to commute. However, as I mentioned, we want that the resolution is isomorphic to the module. So we have to formally invert those maps. So those are the quasi-isomorphisms. So with yeah. So what's the structure that we need to build things? So what the first thing, there is this functor sigma, which is called the suspension. That's an autoequivalence of T. And in the derived category, that's just the shift of the complex. All we do is shift the complexes. And the second thing, why it's called triangulated category, is we have triangles. So we have these so-called exact triangles. They look like we have three objects, x, y, z, and we have three maps, f, g, h. And that's just a distinguished class. So this is part of the definition of a triangulated category, saying which these are. And in the derived category, those are all up to isomorphism of the form, you take any chain map, no quasi-isomorphisms involved, and then you take the mapping cone. So basically all the exact triangles look exactly like this. And now if we want to use these exact triangles to start from one object and generate other ones. So maybe let's do an example. So let's say in the derived category of a commutative ring, let's take two elements. Then I can view R as a complex concentrated in degree 0. I'm just going to write R. I'm not going to write all the zeros along it. And I can look at the map given the multiplication by A. We can ask, what is the cone of this thing? So this is an exact triangle. And the cone, I like to think about it, if you write the complexes on top of each other, you kind of just make the top one lie down on the one below. So we have R, and then we just, this is the complex, lots of zeros. And we all know this complex, it's a Koszul complex. So somehow we started with the ring and we got a Koszul complex. So we have some type of generation, some type of building. We could do this again. Why not, right? We can look at multiplication by B of the Koszul complex on A. I just write cone, and then this is an exact triangle. And for the cone now, we get the original one. And then the one on top, we have to lie down. So we have to put it to the left. And we get AB and B minus A. And this again is a Koszul complex. Depending on your sign convention, it's just Koszul complex of AB, or you might add a sign, up to you. So we now got a Koszul complex in 2 variables. So let's make this construction somehow a bit more explicit. Okay, go back. Okay, let's go back to a triangulated category and let's start with some object. In examples on the right, that object was just a ring concentrated in degree 0. So now there is the thick subcategory generated by G. This is the smallest subcategory. That contains G. And that's closed under a couple of operations. And that is direct summons. So for example, if G is the ring, we get all projective modules because I'm also closing it under direct, under direct sums, finite. Then suspensions and desuspensions, which just means we're allowed to move the complex left, right, doesn't matter. We're supposed to do that. And then it satisfies the 2 out of 3 property. This means if you have an exact triangle and 2 objects in an exact triangle lie in thick of G, then the third one is as well. Okay, and now what we want to do, we kind of want to filter this category to give us like steps. So what we do, we say thick 0, it's just 0. Then thick 1, we want it to contain G, but we're also closing it under under kind of the first properties, direct summons, finite direct sums, suspension and desuspension, but no 2 out of 3 property yet. Containing G closed under. Sorry, I'm writing it just a bit shorter now, but in some words. And now the interesting thing happens. Now we kind of want to glue things together as we did for the example on the left. For an example on the left, we have.
What's the middle thing?
Oh, this closed under summons, direct sums, suspension, desuspension. So basically just the same thing. This part is the same as this. So basically what we, with this definition, the ring itself is in thick 1 of R. And gluing them together, we want to kind of land in thick 2. So this should be in thick 2.
I don't understand.
Yeah.
So thick 0 has the 2 out of 3 property, thick 1 doesn't.
No, none of them have the 2 out of 3 property. Sorry, this one doesn't have a number.
Okay.
So these will turn out to give us a filtration. So at the end, this will be the union of all thick ends. Like if you look at all the modules that have finite projective dimension, then just filter it by less than or equal to n. Yeah. So now we get thick n, and those are all objects that we can kind of put in the middle between thick 1 and thick n minus 1. So there exists an exact triangle x, y, z. We have to kind of allow direct summons as well. So y plus a y plus something, and with x in thick 1 and z thick n minus 1. So somehow we're just taking one in the previous step, and we just glue something to it. And this definition is very robust. So we could replace 1 and n-1 by I and j, and I and j is equal to n. So we could just split them up. It's very robust. And then level or generation time is just the smallest n such that an x lies in here. Such that x and this is the generation time that I mentioned in the title. Yes, please.
I'm struggling a little bit with connecting the example to this because in the example it looks like the x is r and it's in thick 1, and z is the cone and it's in thick 2.
Okay, so the thing you could do, we can just rotate this, right? So the suspension of r, right? So that's why it technically doesn't matter in which order it is. But yeah, good point. This might have been the most useful thing to do. Thank you. And now I kind of gave you a bad example because now we're gluing two things together that are in thick 2. So the cone will only be in thick 4, sorry. But you can actually do better because we all know the Koszul complex actually just has like 3 terms. So if you glue this together, it's like first you take R, then you glue the 2 copies of R to it, and then you glue R to it. We can actually do better. So we can do better. In general, the Koszul object on 2 variables is always in thick 3. So this means that the level of the Koszul object is less than or equal to 3. And this depends a little bit on the situation, whether it's equal to 3 or not, what A and B are. So if you take A and B to be 0, it's going to be 1. But if they're regular, for example, it would be 3. Okay, I think I have now 2 minutes left to actually tell you the results. So actually, wait, let me mention one thing. The point why I made the motivation at the beginning, the level with respect to R of a module is precisely a projective dimension plus 1. And the Lowy length is precisely the level with respect to the residue field for modules. For complexes, that's not the case. But for complexes, we could also use level as the definition of projective dimension Lowy length. And that is a very robust definition.
Sorry, what does it say? The level of
the level of M with respect to R is equal to the projective dimension plus 1.
Right.
And the Lowy length of M is equal to the level of M with respect to the residue field for every R module M. Okay, what our main theorem is basically the 2 inequalities I wrote down hold in general. So, or fairly general. So let's T be a topological triangulated category. I'll say a word about that in a moment. Thank you. Then the level, I should probably put tensor triangulated category in here. We need a tensor product. So the level of a tensor product with a tensor product of generators is bounded above by the level of x with respect to g plus the level of y with respect to h minus 1 for g for all these objects in T. Yeah, so let me just say, so for topological, I just want to say these contain all the algebraic ones. which might not be helpful either. But an algebraic triangulated categories, those are the ones that for us come up in nature. Like derived categories, stable categories, they are all fine. So basically, we're usually fine. But this is kind of the issue that triangulated categories are not always great. But yeah. Okay, so I don't think I have time to tell you about Koszul objects. The basic idea is Koszul objects generalize Koszul complexes. They are very useful if you look at support and things like that. And basically, we show this inequality in general, that if you take a Koszul object on multiple elements, the level is bounded above by like the number of elements plus 1. Okay, I think I'll stop here.